our project is exploring state-of-the-art object detection models. And I'm Jake Barney, and this is my partner, Stephen Fields. So the goal of our project was to survey different real-time object detection algorithms, including one-stage detection models. So we chose SSD, or single-shot detector models, as well as YOLO, which is you only look once. So our three main goals were to examine the model architectures, to explore their performance in different environments, like different GPUs versus the CPU, as well as investigate the different model accuracies. So the first model, the SSD model, was built in 2016 and introduced in a paper by Wei Liu. And the way this model works is it's actually built on top of another model, the VGG16 model, which you can see on the top right. So that it uses that model up until the convolutional layer 5-3, and then builds everything else onto the rest of it. So that portion is used for feature extraction, which is used to create a set of feature maps for the rest of the model. And then below on the architecture for the SSD model, you can see the various convolutional layers, which are used for finding the bounding boxes and object detection. And so what that's doing with these various sizes of convolutional layers is it's moving different sizes and shapes of that bounding boxes along the feature maps to look for potential objects. And so if it detects what it thinks is an object above a certain threshold, it will keep that and pass that on to the post-processing. And then in post-processing, we use non-maximum suppression. So what it's going to do is it's going to use another metric to decide if any of the boxes are overlapping too much. And if they are, then it's going to take the maximum of those two or multiple and keep that one. And then get rid of the rest of them. And so the metric it's using for that is the mean absolute precision. And so for our tests, we both did some of our own testing as well as grabbed some information online from other people's tests. And so what we use for SSD is the SSD mobile net. So instead of using the VGG16 as was done in the original paper, this uses a mobile net, which is a lighter weight model. So that can be more easily used on something like a Raspberry Pi. And the model ran significantly faster on the GPU accelerated hardware. So for those we used for a local machine, we used GPU, we used a GeForce 2070, as well as Google Colab with a GPU hardware accelerator. And so the slower one was just our basic Raspberry Pi, and that does not include a GPU. So as expected, that one performed a lot slower. Our test on the right did perform a lot slower than other tests. So as we can see on the left, from a test done online, we can see some inference speeds like 27 milliseconds, 26 milliseconds, which is a lot faster. The reason that is a lot faster is because in our tests for the SSD, we used an OpenCV detection model class, which also includes pre-processing in the inference time.
Moving on to the YOLO v7 architecture, starting off, YOLO has been iterated on quite a few times in the last 6 years. The first model was released in 2016 and contained 24 convolutions. The latest iteration contains over 105. And although this number of convolutions has grown significantly, it still improves upon each iteration. Lately, the addition of the ELAN or extended efficiency layer aggregation network helped it out to improve training and inference speed. This network essentially allows them to shorten the length of the deviations or derivatives in order to minimize the training of the network. They also added in a lead head auxiliary head architecture that has helped out accuracy. The lead head determines what class each object is, and the auxiliary head is kind of an in-between between the input and the lead head that also predicts the class and kind of tries to help the weights remain relevant from the beginning of the network. On the next slide, we have an overview of different versions of the YOLO model. You can see YOLO v4 had 64.4 million parameters, while YOLO v7 has 36.9, which was a 43% improvement overall. There's a bunch of other statistics here that you can feel free to pause and look over, but one more worth pointing out is YOLO v7 Tiny is shrunk down to 6.2 million parameters. On the next slide, you'll see a graph of our results. The base YOLO v7 model performed at over 100 inferences per second, while the YOLO v7 Tiny performed at well over 200 on both platforms, with locally on a 3060 inferencing at almost 500 images per second. While tangential to the project, it's apparent that consumer graphics cards have started to overtake some of the older AI cards, like the Tesla T4 that's available for free in Google Colab. On the next slide, we have some of the results of running the YOLO algorithm on one of their test images. Although also with pointing out, the base model has a mean average precision of 0.497, while the Tiny model had mean average precision of 0.36. Finally, on future work and setbacks, initially we wanted to experiment with more models and explore their architecture, as well as test on more single board computers. We ran into some setbacks with that. Namely, we had a lot of trouble setting this up on Raspberry Pis due to version mismatches, as well as Jetson Nano recently hit end of life, and that was the only other single board computer we had that also had a GPU. With the Nano, we just ran into issues with Python versions and the Pillow package not being available on a Python version lower than 3.7 at the time. We also ran into a slight setback with team downsizing. One of our team members unfortunately had to withdraw from the course, so that kind of set us back overall on our project. On the last slide, for our conclusion, we've discovered that one-stage detection algorithms are at the state where they're good enough. They definitely have applications where they could be really beneficial, specifically with just detecting things in general, but they aren't performant enough, in my opinion, to be preferred for like a robotic scenario, unless you have something more computationally powerful than most single board computers. That being said, some of the higher end NVIDIA Jetson lines might be suitable for this, but Raspberry Pi certainly is not. And we've also learned how rapidly of an evolving field this is. Object detection. I mean, just since YOLO v7 was released in July of this year, and there have already been, I think I saw 8 or 9 other papers on it, and it's December. So yeah, very rapidly evolving fields. And that sums up our project. Thank you for listening, and I hope you guys learned something.